Boldly going where no science show has gone before. The Naked Scientists.
On The Naked Scientists this week, how the Asian monsoon season takes pollution to new heights, why swine flu spared the elderly, how marine mollusks inspired new lightweight materials, and how the heart comes by its coronary arteries, a discovery that could provide new ways to bypass clogged vessels. That's all coming up. I'm Ben Valsler, and this is Dave Ansell.
We're also looking at the science of weather. We'll find out how aeroplane contrails can create clouds, why insurance companies need the finest weather forecasts, and how you can steer a hurricane.
Also in Kitchen Science, we'll be making our own rainbow, and Diana has a question of the week that we can really get our teeth into.
Now, my question is, I've heard that a dog's mouth is cleaner than a human's. And I'm wondering if that's true, or is it that the normal flora of a human is more virulent than a dog's?
So chew that question over, Babum, and let us know if you know the answer. If you want to get in touch about that, or with any other questions or comments, we would love to hear from you. Send us an email to chris@thenakedscientists.com, or you can tweet @NakedScientists.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
This is The Naked Scientists with me, Dave Ansell.
And with me, Ben Valsler, and I will start off this week with a paper published in the journal Science that shows that pollution in Asia gets pushed up into the stratosphere by hitching a ride on the monsoon. William Randall at the National Centre for Atmospheric Research in Colorado and an international team including researchers at York and Edinburgh universities used satellite imaging to keep track of something called hydrogen cyanide. Now, this is a pollutant associated with burning that usually stays mainly up in the troposphere. That's the lowest portion of Earth's atmosphere. Hydrogen cyanide is a particularly apt choice because usually most of it is lost to the ocean. There's relatively little high up in the troposphere, so with normal circulation, there'll actually be relatively little that can move up into the stratosphere. In general, air is circulated from the troposphere up to the stratosphere. That's the next layer of the atmosphere. It starts somewhere between 10 and 50 kilometres. And usually the air moves up into there at the tropics. And that's as part of something called the Brewer-Dobson circulation. But this paper shows that the Asian summer monsoon acts as a very effective pathway for rapid transport of air upward from the Earth's surface. And that in turn provides a route for pollutants like black carbon, sulfur dioxide, nitrogen oxides, and all of these get to gain access to the stratosphere. The route is there because the monsoon itself contains a strong anticyclonic vortex. That's a circulation of winds around a high-pressure region that pushes air up from the ground. It's a little bit like a hurricane, but it turns in the other direction. Once pollutants get up into the stratosphere, they're very likely to be moved around the world, and they impact on atmospheric chemistry, such as reacting with ozone. In fact, movement in the stratosphere is far greater than movement between the troposphere and the stratosphere itself. So this horizontal movement is actually greater than the vertical movement. It also creates a barrier between some pollutants, such as HCN, this hydrogen cyanide, and the ocean, which acts as a sink for them. So up in the atmosphere, without contact with the seas, hydrogen cyanide has a lifetime of about 4 years. Now, this does give us some great cause for concern, because not only is the industrial pollution of Asia increasing at an unprecedented rate, but now it looks like it has a direct pipeline up to the stratosphere. So pollution from Asia can actually have a greater effect on atmospheric chemistry than we've ever thought possible.
And I guess the last big story about pollutants getting up into the stratosphere was CFCs getting up there, causing havoc with the ozone layer as well.
Exactly, yes, and changes in atmospheric chemistry can be very important, and of course the ozone story is a very well recognised story.
Now, fresh water is one of the most fundamental needs of humans, and a group from MIT has found out a new way to make it. Many natural disasters can remove our source of clean, fresh water, which is absolutely lethal for us. But one inexhaustible source of water is, of course, the sea, but the salt makes it no use for drinking. There's various ways of desalinating this water, but most of them don't scale down very well. So if you had lots of people in a disaster area, you can't give them out a little water purification kit very easily. The best one of those so far is reverse osmosis, essentially filtering the salt out with a special membrane. This requires large pressures, which needs a pump, and membranes tend to get gummed up by contaminants. Now, Sung Jae Kim from MIT and colleagues have come up with an alternative. Instead of using a membrane to separate the salt from the water, they're using electricity. They made a Y shape of very small channels, about 0.5 millimetre wide. The dirty water comes up the stem of the Y. On one of the two arms is what's called a Nafion nanojunction, made of a material called Nafion. This is a material which will let positively charged ions flow through it, but not negatively ones. This means that you end up with an area where no ions end. It's formed this complicated process, which means an area with no ions in it, and all of the ions get pushed up the other junction of the Y. Meaning you get fresh water coming down the first arm of the Y, and charged species and ions and bacteria all end up going out through the contaminated one, with 99% of the water is removed. It isn't quite as energy efficient as reverse osmosis, but it's intrinsically a much smaller scale thing, and you could maybe build a machine consisting of maybe 1,600 of these junctions to purify about 15 litres of water a day, which is enough for a family. And because the contaminants are all pushed away from the sensitive parts, it doesn't clog up in the same way as a membrane does.
Roughly how much power does it use? You said it's less efficient than a reverse osmosis pump, but usually they're pumped by hand. It might be quite a difficult comparison.
It's sort of using about twice as much energy as a reverse osmosis system. So it's the same order, but not quite as good. But you can scale it down.
Excellent. Now, research looking at the shape of the H1N1 pandemic flu virus has revealed why seasonal flu vaccines don't offer any protection, but it also suggests why the older generation are more likely to have immunity to the pandemics. Two papers, one published in the journal Science by Ian Wilson and colleagues, and the other in the journal Science Translational Medicine by Gary Nabel et al., looked at slightly different aspects of the virus and together made some very interesting conclusions. So, writing in Science Translational Medicine, Gary Nabel and colleagues exposed mice to seasonal and pandemic flu strains from both 1918, what we call the Spanish flu, and from 2009, the swine flu pandemic, and analysed the antibodies that they produced in response. They found that antibodies against pandemic viruses protected the mice from both 1918 and 2009 pandemic flu, but seasonal flu antibodies offered no protection at all from pandemic viruses. They did, however, protect very well against seasonal flu, so essentially they're not protecting against each other. This tells us there's something about the structure of both pandemic viruses that the antibodies can lock onto, something that they don't share with the seasonal virus particles. And they found, and this was then confirmed by the crystal structure of the virus particles published in Science magazine, that the antibodies were attaching to a protein that sits on the outside surface of the virus. This is called the spike protein, so called because it helps to spike into cells and infect them. Interestingly, the structure of the spike protein is very similar in both the 1918 and 2009 pandemic viruses, and they share what we call an epitope. They're nearly identical, and an epitope is a region of a molecule that has essentially a well-defined shape to which an antibody can attach. In the seasonal virus, however, the spike protein is obscured by two sugar groups, and this stops the host immune system from recognising the virus, and is actually one reason why vaccines designed for pandemic viruses don't offer you any protection against the seasonal forms. So not only does this tell us why you don't develop immunity to both types of flu when you've suffered from one, but it also hints at why older people were more likely to be protected against last year's H1N1 pandemic. Exposure to the 1918 strain as a child may well have tuned their immune system to the shape of that spike protein and therefore offered some immunity.
Very cunning virus, that. Now, ceramics, materials like pottery, have all sorts of very useful properties. They're very hard, resistant to heat, and some are very strong. But their use has always been very limited because they're very, very brittle. They're not tough, which means they can't absorb energy from an impact without shattering. As you've probably noticed if you ever dropped a cup or a plate on the floor. And once a crack starts going through the ceramic, there's nothing to stop it keep on going all the way to the other edge of the material. For a while, scientists have been fascinated by shelled animals, things like abalone. Their shells are made up of tiny plates of the brittle ceramic calcium carbonate, effectively limestone, mixed with proteins to give a very, very tough material, which can survive an incredible amount of abuse. This is because a crack can only travel through a single plate, and then it stops at the edge of that plate. Many scientists have been interested in these properties and been trying to make various materials in the lab, and they've made various interesting ones. Now, Andreas Valter from Helsinki in Finland has managed to make a similar structure out of a clay, which is made of microscopic plates, and PVA glue. It's very easy to make and can actually be painted or sprayed onto walls or an aircraft skin. The properties are actually very similar to fiberglass, but it can be applied much more easily, and it's much thinner. And apparently tests with flamethrowers say it's also very fire resistant.
It doesn't surprise me that you've looked at the test with flamethrowers bit. Well, that's really interesting because, of course, we use these... It sounds like it's essentially a laminated material where you have different layers with something different in between. And this is something that we rely on quite a bit in materials.
You're using two different materials. You're using the very, very stiff, strong strength of that ceramic, but the toughness of the PVA long polymer molecules which hold them all together and resist the cracking.
Thanks, Dave. Also in the news this week, a paper in the journal Nature overturns a 100-year-old misunderstanding about how the arteries that supply the heart with blood first develop. Paul Riley from University College London is the author of the News and Views article that accompanied the paper, and he joins us now. Hello, Paul.
Hi.
First of all, what has been the prevailing idea for the last 100 years, if not more, about how coronary arteries actually form?
Well, it's an evolving idea, really. So initially, the coronary arteries are thought to bud off from the main vessel, the aorta, that serves the rest of the body. That was disproven when actually vessels were shown to ingrow into the aorta, so the reverse process. And then more recently, over the last 20 years or so, studies in chicken and quails have shown that a transient organ called the proepicardial organ, which sits just above the developing liver at the sort of base of the heart, if you like, that contributes cells which can give rise to the epicardium, which surrounds the heart, and then those cells subsequently give rise to endothelial cells which make up the coronary arteries. So that's, if you like, that's the most common idea as it stands before this paper.
And so what have they discovered now? What's new about this paper?
Well, a previously unsuspected source, really. I mean, what they've shown is by very carefully tracking individual cells within the mouse heart through genetic tagging, they've shown that cells can emerge from the inflow region, a region where there's a large venous input called the sinus venosus, and that these cells can de-differentiate as vein cells and actually give rise to new cells that then become artery-like and actually form the developing coronary arteries. So it's a completely unsuspected source of cells, and moreover, the fact that they can de-differentiate and change their fate from veins to arteries is the real crux of the finding.
So these cells start out as a vein cell.
That's right.
And then they turn into just a general cell. And what do they do then? Do they migrate themselves, or do they grow through into the tissue?
Yeah, I mean, you have to get the de-differentiation, the change of these sort of vein cells. They have to de-differentiate to become more progenitor-like, if you like. And then they have to migrate inward and start to form a plexus where they're connected into the muscle tissue of the developing heart. And then they become fated to become arterial cells. So they start to turn on characteristic markers which suggest that they are becoming arterial-like. And that network then progresses throughout the developing muscle of the heart to form the coronary artery network.
Now, what does this tell us with regards adults with heart conditions? Because all of this work has been looking at the embryonic development, where these arteries first come from. But of great concern to many, many people is what happens when these arteries become blocked or become damaged later in life as an adult. Can we learn anything from this work that could help us to treat people?
Well, I think there's a very basic principle that if you understand how the heart is put together, both at the coronary vessel side and also the developing muscle, then understanding the cell behavior and the signals that trigger that can be applied to the adult setting. So some of these cells are present in the adult heart, and therefore if we understand how to re-trigger the process of making new vessels, then obviously we're in a position where we can revascularize an injured heart that has lost blood vessels and also muscle, say after a heart attack. So it's fundamentally important to understand how these vessels are made in the first place, to then go back into the adult, track a similar cell population, and then be able to stimulate with appropriate signals to make new vessels. So it's completely translatable, although some way off in terms of the realistic research goal. But this is a major step in the right direction. And through taking these studies further, understanding how they switch from veins to arteries, and understanding the signals from neighbouring tissues that allow this to happen, should be able to then be fully translated into the adult setting and hopefully set up a therapeutic by way of making new blood vessels.
Very promising stuff. Obviously very early stages, but very, very promising. Well, thank you ever so much, Paul. That was Paul Riley from the UCL Institute of Child Health. You can find his News and Views article and the paper itself, which is by Christy Redhorse and colleagues at Stanford University. You can find them both in this week's Nature magazine.
Distilling the best science. The Naked Scientists.
You're listening to The Naked Scientists with Ben Valsler and Dave Ansell. If you'd like to contact us through Twitter, it's @NakedScientists, or you can send us an email to chris@thenakedscientist.com.
Thank you, Dave. This week we're talking about the weather, and coming up later we'll be exploring the idea of steering a hurricane out of harm's way. But first, most of us are familiar with the long trails left behind by aeroplanes as they pass overhead. I can almost see some through the window here. But those trails, or contrails as they're called, it seems can actually give rise to clouds. Now, we're joined by Dr. Jim Hayward, who's from the Met Office. Now, thank you for joining us, Jim. My first question, really, to get a broad idea, is how are clouds normally formed?
Well, clouds almost invariably form when the air that contains the water vapour cools. Cooling is almost always initiated by a lifting action. For example, air flowing over mountains can cause the air to cool to such an extent that the water in it condenses, forming a cloud. Alternatively, you can have things like cool air undercutting warm air and forcing it to rise in frontal systems associated with low pressure systems in the mid-latitudes. So really it's just a case of air being forced to cool. The relative humidity, as meteorologists call it, exceeds 100%, and the water in it condenses.
And when we see these big lines up in the sky, these contrails from aeroplanes, what are they actually made of?
Obviously, most clouds that we can see from down here are made up of water droplets. Contrails tend to be made up of ice crystals that grow when the conditions are favourable.
And how do these then go on to create a cloud?
What you can get is, under certain conditions, which is basically cold and moist conditions, the ice crystals that are initially formed by the aircraft contrail can grow. It's a bit like physics experiments that you probably did at school, where you grew crystals of copper sulfate or things in supersaturated solutions. That's exactly what's happening here. When the conditions are right, when it's cold enough and moist enough in the upper atmosphere, then the crystals that are initially injected can just grow in tremendously and spread with the meteorological flow.
So we're not talking about lots of individual particles like we would be for, I assume, a normal cloud. This is actually a very large ice crystal that just happens to be light enough to float about. Is that right?
Well, the ice crystals, when they're initially injected, are about a thousandth of a millimetre, typically in terms of size. But as they grow, they can actually get many times that, up to about 100 microns. So they do form very large crystals, which are important in sort of the Earth radiation budget.
These clouds obviously are a bit different to normal clouds. How do they affect the weather? Are they rain clouds? Are we likely to see rain from them, or just perhaps a bit of shading, or really will they not affect us much at all?
They do affect us in terms of the amount of sunlight that they let through. That's quite important. They tend to reflect sunlight back out to space and lead to a cooling of the weather and consequently the climate. But they also trap outgoing long-wave radiation, so heat radiation, if you like, rather like the greenhouse effect. So there's these two competing effects. You've got the reflection of solar radiation or sunlight back out to space, and you've also got a greenhouse type of effect. And what's critical is really the balance between the cooling from the reflection of solar radiation and the warming due to the greenhouse type of effect of these crystals.
So if they need very particular conditions in which to form, does this mean that certain flight paths are actually more likely to create these clouds, and therefore we're more likely to have this warming effect or this reduction of sunlight effect in certain areas?
Yes, that's right. I mean, one of the areas that's particularly good for forming cirrus type of particles, these ice crystals, actually coincides with the air traffic corridors, particularly the one linking North America with Europe. That's a particular area that's good for crystal formation and crystal growth.
We've had a very, very relevant question from Neil Briscoe. Now, he said that he heard a while ago that thanks to the 9/11 attacks, when they grounded all the flights, people were able to work out that contrails during daylight hours helped to prohibit warming by reflecting light back out into space. But during night time, they actually increased warming. Is this the same stuff that we're talking about here? Does it matter whether it's day or night?
Yes, it does indeed. It's exactly what that question's about. Really, we're talking about a cooling, if you like, from the reflection of sunlight and a warming during the nighttime, which can cause a reduction in what's called the diurnal temperature range. After 9/11, there was certainly evidence of a reduction in the diurnal temperature range from a particular study. But it's quite difficult to disentangle that signal, if you like, from the natural meteorological events that can occur. And when they looked at it a little bit more detail, it became almost impossible to distinguish from other events that had nothing to do with 9/11. You still could see this signal in diurnal temperature range just due to the natural variability of the atmospheric system.
So it may have an impact that we can't see because it's no bigger than noise.
It's just difficult to detect, that's right.
And speaking of detecting it, how do we actually study these things?
Well, we study it by a number of ways. We've been simulating these contrails and contrail-induced cirrus in state-of-the-science atmospheric models that we use at the Met Office and the Hadley Centre for Climate Change. We've also been having a look at various different aircraft measurement campaigns. I'm involved with an aircraft measurement campaign where we're trying to create contrails and actually measure the amount of reflected sunlight and the amount of infrared heat energy that these contrails affect. So you can do it from a purely modelling perspective, but it's always better to base it on sort of objective measurements.
And just finally, all these contrails obviously tend to stay in one place in the sky. When they go on to create these cirrus-type clouds, do they also stay where they were created, or do we find that they drift across the country and have that sort of effect on a slightly wider area?
Oh, yes. I mean, we studied one particular contrail that was formed by an AWACS aircraft over the North Sea. And what we found was, although that aircraft had only travelled 1,500 kilometres, the area of cloud that it created was actually over 50,000 square kilometres. This area of cloud, this was created last March. You could see quite clearly be advected over the UK and lasted for several hours. It actually lasted for around about 18 hours before the ice crystals started to dissipate.
So that's certainly something to think about next time you're 30,000 feet above the UK. You might actually be making it a little bit cooler for us down on the Earth in the daytime, possibly a little warmer at night. That was Jim Hayward. He's from the Met Office, and thank you ever so much for joining us.
Laying the facts bare. I say. The Naked Scientists.
You're listening to The Naked Scientists with Ben Valsler and me, Dave Ansell. We're looking at the science of weather.
If you would like to get in touch with us, you can call on 0845 30 50 007 or send a text on 07786 20 1960. But if you'd like to contact us through Twitter, it's @NakedScientists, or you can send an email to chris@thenakedscientist.com. Also, you could join us in Second Life, where by the looks of things, they're currently discussing water on Mars. Red Lace Serene has pointed out that what we thought were water channels on Mars may actually be really lava channels, and there's some good discussion of that in the Naked Astronomy podcast this month. And Asterion Cohen has suggested that we send some of the many clouds we get in the UK up to Mars, and that should be enough to fill it with oceans. But still to come, how you could steer a hurricane and keep it away from land, and in Kitchen Science, we'll be making our own rainbow. Dave.
Now, moving away from clouds and over to the extremes of weather, more specifically windstorms. For example, the winter storm Anatole blew through the UK, Sweden and Germany and caused economic damages of approximately €2.9 billion. Much of this was claimed on insurance, and so insurance companies are very interested in predicting these extreme weather events. A team from the University College London's Climate Extremes Group have created just the tool to do this and formed the company Eurotempest to help European insurers prepare for the billions of pounds worth of damage that may be coming their way. Mira Senthilingam went to visit them in London and met the operations director Frank Roberts to find out what they need to know for these predictions and how this weather forecasting data is collected in the first place.
Well, in the first instance, the modelling agencies, that's the national meteorological agencies of any country, and obviously in the UK, that's the UK Met Office, will collate observations from all over the world. I think the Met Office collects about 500,000 per day at the moment, and that can be from any source, so satellites, weather balloons, surface observation stations, buoys at sea, aircraft. And from that, they need to build a complete picture of the atmosphere, because obviously these observations are only taken at certain points. And this is what they call the assimilation process. And they have complex mathematical models to do this. And from that, they will then use what they call their numerical weather prediction system. The atmosphere is broken down into, well, on the surface, latitude, longitude, grid squares, so just as if you were looking at a map, and various levels. So you have these cubes of atmosphere, and you apply then the physical equations to each cube of the atmosphere in order to be able to predict the various parameters that you're interested in.
So parameters such as?
Temperature, wind speed, wind direction, humidity, the amount of rainfall that you would expect, cloud cover.
To what resolution is it usually possible to predict the weather? So what area?
Well, the current global model that the UK Met Office use is on a resolution of about 60 kilometres.
Here at Eurotempest, though, you focus on the parameter of wind speed and essentially then try and predict wind storms across Europe.
Yeah, that's right. We focus on wind specifically because we provide a summary of information not for the general public but to the insurance industry. Severe wind causes, on average, over the long-term average, about 80% of the insurance loss from natural hazards in Europe.
So how do you go about collecting data for wind speed, and therefore what kind of information are you putting together to help insurers plan for windstorms that may be coming up? OK,
well, we take the surface level output from the UK Met Office numerical weather prediction model for wind speed, and from that build up a picture of the wind speed forecast for the country in the coming 5 days. We go out to 5 days. We've also, our customers who are insurance companies have provided us with information about where their insured properties are. So by postcode, we have information about what we would call their exposure. That's the total value of the insured properties in those locations. And then we use what we call a vulnerability model. This is built up from historical observations of claims and wind speeds in given locations, and it's a statistical model which allows us to estimate the proportion of buildings which will be damaged in a given postcode area from a given wind speed. So you can't say necessarily, of course, that this particular building is going to be damaged, but if you've got enough buildings of a certain type in a large enough area, then you can say what proportion of damage is going to occur. We can do that for the country as a whole, for each of our customers, and then they have a good idea of what ultimate payout is going to be from a severe wind forecast.
What kind of wind speeds does it take then to really damage property?
Well, typically serious damage really only begins at about 60 miles an hour, and that's not particularly usual. I mean, it's not an everyday occurrence in the UK. Insurance companies tend to get interested to around about 40 miles an hour, and you can get small levels of damage at those sorts of wind speeds, as you might expect, a few tiles or the odd branch breaking a window or something like that.
Now, in terms of actual damages then and cost, how much damage can be done by wind?
Well, in the UK, on average, it's about £500 million a year, which is obviously an awful lot. You might remember fairly recently, just at the beginning of the month, there was a severe windstorm in France called Windstorm Cynthia. Now, the estimates for the losses from that are well over £1 billion.
So, as well as helping insurers prepare, essentially, for maybe a large amount of payouts that are about to come out, how else does this benefit them?
They can prepare for the large amount of payouts, but of course, if there's a severe event, there are likely to be an awful lot of claims coming in all at once. So it helps them to manage their human resources to make sure that they've got enough people in their call centres to be able to answer the phone, to answer the claim from each of their customers. It's extremely important to them that they're able to settle claims very quickly from a customer satisfaction point of view, but also from the point of view of the longer that damage is left unfixed, the higher the bill tends to be ultimately. And we also provide a system for insurers which allows them by postcode and date to interrogate the observation data set. So when a claim comes in, they will be able to look at this system and they'll see the distribution of observation stations around the postcode, and it will report the wind speed or the rainfall or whatever it might be. So they can check back to see that there were damaging conditions prevailing on the day that the damage happened, and then they can validate the fact that the damage that's been reported by the insured is actually consistent with storm damage.
But now what makes this vulnerability model then better than insurers just keeping an eye on weather forecasts?
Well, the public and media weather forecasts are specifically designed for public consumption, for public safety, and that will be couched often in terms of we may see 80 miles an hour gusts, for example, at a peak. It doesn't really say in any great detail where exactly that might be expected, and that's the sort of high-resolution information you need to predict for an insurer. So translating a verbal media forecast into a forecast of loss is actually very difficult for anybody to do. And in the past, we have examples from customers who said had they only had the media forecast available and tried to interpret that in terms of what their exposure was, they would have been out by a factor of 10 compared to what we were correctly saying.
With all that saving, hopefully our insurance payments will be more efficient in the future and hopefully a bit cheaper. We'll have to keep our fingers crossed on that one.
Indeed we will, yes. That was Frank Roberts, Operations Director at Eurotempest, talking to Mira Senthilingam.
Keeping you abreast of the world's best science. The Naked Scientists.
This is The Naked Scientists with me, Ben Valsler, and with Dave Ansell. If you'd like to contact us via Twitter, it's at Naked Scientists, or you can send an email to chris@thenakedscientists.com. Dave?
Now we're going to go and talk to Dr. Moshe Alamaro from MIT, who's come up with a plan that could, in theory, be used to steer one of the most powerful forces of nature, the hurricane, away from danger. Hello, Moshe.
Hello. Hi.
I guess best to start, what exactly is a hurricane and how do they form?
Hurricanes in the Atlantic are formed in mid-Atlantic, eastern Atlantic, and sometimes inside the Gulf, the Caribbean Gulf. And then they travel west and eventually northwest and ultimately north. And they are part of the global circulation. In fact, in an active hurricane season, the temperature in Iceland is higher than usual. So hurricane is an essential part of the global circulation.
So they're moving heat around. So what's actually the structure of a hurricane itself?
Well, this is the description would take too long, but the genesis of hurricane is not fully understood. It starts as a tropical storm. There are about 100 tropical storms in the Atlantic a year. We cannot intercept all of them because they are beneficial. They bring rain to Central America and South United States. So if ever we are going to intercept hurricane, it will be when the hurricane, because only 10% of the tropical storm about become hurricane, then we will need to intercept the hurricane when it is in full power.
So how are you intending to intercept them and affect them?
Okay, just to give you some number, the power of hurricane is on the order of 10 million megawatt. The power of the combined electric grid of the world is only 3 million megawatt, which is about a third of the typical power of hurricane. So fighting hurricane head-to-head is hopeless. But we know that hurricane has some Achilles heel, and hurricane is not robust in its track and its intensity. So we found by simulation that if we change slightly the atmospheric conditions surrounding of the hurricane, we would be able to divert the hurricane from its track to another track that might be less damaging, less dangerous.
So hurricane is actually quite sensitive to the conditions around it. Is this the reason why they're so hard to predict where they're going to go naturally?
Yeah, now it's less hard to predict because we have a very good information about the surrounding atmospheric conditions. But as I said, it's enough to change slightly the temperature, humidity of the atmospheric condition to cause change, could be substantial change. And that was found through some computer simulation that we have done. Now, about the physical means to create perturbation to the hurricanes, there was a program which was ongoing until 35 years ago by NOAA, and that program was called the Storm Fury Project. And in this project, the cloud of the eye of the hurricane were seeded by silver iodide, and it was a project that was ongoing for 23 years. What we tried initially is to, instead injecting silver iodide, which is a nuclei for freezing, to inject ice by carrying water in airplane in high altitude, freezing the water, and then using the ice instead of the silver iodide. Eventually we found that the project Storm Fury was abandoned because it was already found that there is ice in the cloud, and adding additional ice or silver iodide would not make any impact. But nevertheless, this development led to important technology that has nothing to do with hurricanes. The second implementation or experiment that we did is with a film which is called monolayer. It's a material that you place on water. It propagates and propagates until the width of the material is literally one molecule. And it's enough 25 grams of this material to cover a square mile of water surface. The monolayer is effective up to 30 miles per hour, and it's not effective in hurricane speed.
So basically trying to affect the evaporation, which would drive the hurricane, hot water vapor rising, which is what actually powers the hurricane. Exactly. The water vapor rising and condensating and releasing of the evaporation heat is a source of the energy. So what have you found which might actually work? Until now, we didn't find any method which is working. We are right now working on our fourth method, which is spreading carbon black or soot on the top of hurricane from airplanes, and we have shown that this might change the thermodynamic of the hurricane, lessen the intensity of the hurricane, and or be able to divert its track from one track to another. Brilliant. How practical is this? How many planes would you need? And I'm guessing the other big problem is if you drive the hurricane into somebody else's city, they're going to be unhappy. Yeah, there are major legal, ethical, political, and international issues with hurricane, because if hurricane comes to one region, say populated region, and then we divert it to less populated, but in the less populated some people are damaged, they will claim that the hurricane is not any more act of God, but we caused it. And that could cause some really serious legal issues. Thanks, Moshe. That was Moshe Alamara from MIT on how we could theoretically steer hurricanes if we can get the lawyers out of the way first.
Well, Silverwing Benoit in Second Life said that wouldn't moving a hurricane help some areas and hurt others. It certainly seems that there's a political, legal thing that we need to do. And Redley Serene pointed out that the hurricane needs to go where it needs to go because it's an energy transport and balance mechanism. Now, earlier this week, we took advantage of the very few sunny spells that we've seen recently to record this week's colourful Kitchen Science.
We've got a really simple experiment to do today to explain one of people's favourite pieces of weather, the rainbow.
Rainbows are very pretty. The weather has to be right, of course. So is this an experiment that we can easily do?
Well, all you need is a plant mister, one of those sprays which uses a spray of water droplets, and a sunny day, which is looking slightly more dubious at the moment.
I think we may have a few minutes before the sun goes behind a cloud. So with your plant mister, what do we need to do?
OK, you really want to find somewhere where it's just on the edge of shadow and sunlight. Take the plant mister, you want to stand with your back to the sun and then spray into the bright bit near the shadow and look through the droplets of water into the shadow.
I see now. Immediately upon you doing that, there's a fine mist of water in the air, and I can clearly see those distinctive colours of the rainbow and in the right curve shape just in front of you. It's not quite as pretty as a proper rainbow, though.
Well, a proper rainbow's got more water in the sky, basically. There's a limit I can do with this mister.
OK, but it definitely works. You've made a rainbow using just a plant mister.
And another interesting thing is move your head whilst I'm spraying.
I can see the rainbow moves as well. It's not just stationary in one place in front of me. It actually seems to move through this mist relative to the background.
Yeah, you should find it actually moves with you rather than with the background.
So that, again, is a bit like a real rainbow, because when you move towards a rainbow, it seems to move as well.
Yeah, and why you're never going to find the end of a rainbow to find that pot of gold.
Well, I don't really think we can get away with looking at the scientific basis of the leprechaun's pot of gold, but what is the science of a rainbow?
So you've got the sunlight coming from the sun behind me. When I'm spraying, that sunlight comes down and hits the droplets of water, and then somehow that's reflected back into our eyes and we can see something interesting. And because we're looking at a dark background, it's not getting completely washed out by the bright reflected sunlight from the cars and things in the background.
So that was why it was important to do it facing a shadowed area. But what is actually happening inside those droplets of water? How does the light get reflected back?
Well, inside I've got some demos which should make that a bit more clear.
OK, well, we'll go inside, and that gets us away from the vagaries of the sunlight, which has once again gone behind a cloud. So we've come inside into quite a dark room, but how on earth can we be looking at rainbows with all the curtains shut?
In order to understand a rainbow, you've got to understand what's happening in a single droplet of water. So what I've done is I've made a model of a single droplet of water. I've got a nice big bright light to be a model of the sun. And because making a spherical lump of water is very difficult, I've got a cylindrical piece of water, basically a glass of water, on the table.
Your glass of water is going to act like one of the many hundreds of thousands of droplets of water that we used outside to make a rainbow. But what should we expect to see?
OK, so what's going to happen is you want to get in the similar sort of place where you see a rainbow. So you want to have the light over your shoulder, and you want to be sort of maybe 30, 40 degrees off the line of the sunlight hitting that glass. And what's going to happen is the sunlight is going to come into the glass of water. It's going to get bent a bit as it slows down and enters the water. It's going to reflect off the back of the glass, then come out and get bent again as it leaves. If you get into the right position and look for that light which is getting reflected back.
Because the glass is on a table, I'll have to crouch down for this, and there's a very bright spot of light. It looks like it's bouncing off the inside of the glass.
That's right. Now, if you move your head into different places and watch that spot.
So as I move over to the left, the spot looks like it's moving over to the edge of the glass, and it's gone a bit blue. Oh, hold on. As I'm moving, it's now gone a very bright orange, almost a sunset colour. So as I move along, the spot changed colour.
Yeah, that's right, because different colours of light are bent, refracted, slightly different amounts by water. And this means that the light leaving will leave in slightly different directions for different colours of light. Therefore, it means that the raindrop will look different colours depending on where it is with respect to you.
So in a real rainbow, why do we see one clear spectrum? Why don't we just get a big blur of colour?
Well, when you're looking at the raindrop, what you're doing is looking at millions of droplets of rain. And each of those droplets of rain will look different colours at a certain range of angles. And so if you see a raindrop which is at 40 degrees with respect to the sunlight, it will look red. And at a slightly larger angle, it will look orange, then yellow, then green, then blue, and then indigo.
So we're actually seeing essentially one tiny fragment of the spectrum from each drop of water that we see. And that all adds up to be the beautiful colours of the rainbow.
Yeah, that's right.
How does it form this beautiful arc?
Because this glass isn't a sphere, it's a cylinder, all you can see is the different colours in two lines at either side of the glass. But if it was a sphere, you'd be able to see the red light, for example, in a cone symmetrically around the sunlight coming and hitting the raindrop.
So because they're spherical, instead of there just being one vertical plane in which I can see each colour, which is what's happening with this glass, it actually forms a cone shape, essentially a ring. But how does this add up to give you the distinctive shape of a rainbow?
Well, this means that if you look at a raindrop which is above you, then you will see the bottom part of its cone. If you look at a raindrop over to the right, you'll see the left-hand side of its cone, and to the left, the right-hand side of its cone. And all those add up. So the raindrops you see which are red are in an arch. In fact, it's actually a whole circle. If you could see the rainbow below you, you'd see a whole circle of rainbow.
Now, sometimes you see an incredible effect where you actually get a double rainbow. You get two rainbows, one inside the other. What's going on there?
Well, that's when you get an extra reflection inside the raindrop. Instead of it just reflecting once at the back, you get two reflections. So it forms a rainbow at about 50 degrees away from the sunlight rather than 40 degrees.
Well, thank you, Dave. I wouldn't have thought you could demonstrate a rainbow using just a glass of water. So next time you see a rainbow up in the sky, instead of looking for a pot of gold, look to see if you can see a second, fainter rainbow outside it. And that's all down to the physics of light and water.
And you can find out more about that online at thenakedscientist.com/kitchen science, along with loads of other kitchen science experiments you can try at home.
It is one of my favourite parts of the week, doing kitchen science. Now, this is The Naked Scientist with me, Ben Valsler, and with Dave Ansell, and we've had a couple of your questions that we want to deal with, talking about hurricanes and ways to stop them. We've had a question from James Hamlin. Now, he asks if it's tangible to churn up cooler waters from the deep, from the depths of the sea, and use that to cool the surface water, and therefore use the cooler water to prevent or calm hurricanes. Dave, what do you think?
I mean, in theory, if you could reduce the temperature of the surface of the sea, that's going to give less energy to the air above it, less upwelling of air. So you're going to get much weaker upwelling, and you could stop a hurricane forming. However, hurricanes, as Moshe was saying, can form anywhere over the whole of the Atlantic, all the way into the Gulf of Mexico. So you'd have to cool down the whole of the surface of the ocean, which is getting to be a ridiculously huge engineering job. Also, it would only work for a few years because eventually you'd warm up the deep ocean, you'd cause all sorts of havoc, you'd alter the balance of nutrients in the ocean. And as Moshe was saying, small storms are actually very important for us because they bring water, rain into the whole of the west side of the Atlantic.
Not to mention the fact that the temperature structure of the oceans are actually incredibly important for the currents and things like what we call the conveyor system that moves warm and cold water around the world.
And if you're not careful, you'd end up freezing northern Europe where we are because you might break the North Atlantic conveyor, the Gulf Stream.
That's another reason why this is an ethical and legal minefield. Not only could you send a hurricane into somebody, but you could also freeze England by accident. We've had another question, thinking of temperatures and water, from Ivis Bo Davis, and he wants to know at what temperature can you split water into hydrogen and oxygen by thermal means. Now, Dave, I know that you do something in your hands-on science group where you split water into hydrogen and oxygen electrically, but how could you do it with just temperature alone?
You can do it electrically with about 1.3 volts of electricity. However, to do it thermally, you've got to heat it up to over 2,000 degrees centigrade. It's one of these things whereby the hotter you get, the more complete the dissociation. You split the molecules up. It is actually a suggested way of making hydrogen. You heat up water at very high temperatures. You then have to somehow separate out the hydrogen and oxygen because otherwise it's easily hot enough to burn and condense back to water again. So you need some kind of membrane to separate the two, which apparently do exist, special kinds of ceramics again. And you can separate the two and you can get hydrogen out. But yes, it can happen somewhere above 2,000 degrees C.
And would it help if you were to add some kind of, I know that they've been looking at using platinum to help do this. You find catalysts that help reactions happen at different temperatures. Could we find the right catalyst that therefore meant we didn't need to be quite so hot as 2,000 degrees?
Catalysts certainly help with electrolysis, doing it electrically. My knowledge of high temperature chemistry is very limited, but I think the fundamental thing that you're working against is the actual energy you need to split apart a water molecule, and thermally that's an awful lot of energy. So I would be surprised if you could gain that much.
Thank you very much, Dave. Something to think about. And now, with a subject that you can really get your teeth into, here's Diana O'Carroll with our question of the week.
This week, which of these bites takes the biscuit?
Hi, hello, my name is Paige. I am a student at University of North Texas in the U.S., and I love the podcast of The Naked Scientist. Now, my question is, I've heard that a dog's mouth is cleaner than a human's. And I'm wondering if that's true, or is it that the normal flora of a human is more virulent than a dog's? Thank you.
Is Rover in the clear?
I'm Dr. Nick Brown, and I'm a medical microbiologist at the Health Protection Agency Microbiology Laboratories at Addenbrooke's Hospital in Cambridge. Well, you might think that a dog bite would be the more dangerous, and certainly, of course, in terms of trauma and particularly related to attack, they can be very nasty. But actually, in terms of infections, then human bites have a very high incidence of complications, and so many people would actually say that human bites are nastier than dog bites. So all our mouths and all animal mouths are full of bacteria all the time, and the sort of organisms that cause this infection are the things like streptococci and staphylococci particularly, but the importance of the bite, of course, is that because of the teeth and the trauma that's associated with them, then those organisms can be introduced deep into the tissues where they can replicate and cause infections.
So, is it possible to say definitively who has the dirtier mouth?
I'm Andreas Karras. I'm a consultant microbiologist with the Health Protection Agency in Cambridge. The question about whether a dog bite or human bite is worse would depend largely on where in the world you are. If you were in the developing world, rabies becomes a major factor, and you would much rather be bitten by a human where rabies is much less likely. If you were in another part of the world, it would depend a lot on the site of the bite. Human bites, in my experience, have always much worse, as they're often on the face, genitalia, really bad parts of the body, so probably better to go for dog. But if you had an equivalent bite, so the same size bite on, let's say, your leg by a human or a dog, it's probably much of a muchness. Generally, humans probably have a more diverse flora, larger number of different organisms. Dogs have a lower number of organisms. But either of their mouths would have hundreds of different bacteria in them of different types. And the ones that do the damage are really anaerobes. Dogs have a particular organism called Capnocytophaga canimorsus, which can, if it gets into your bloodstream, can give you very severe blood poisoning. And there's a lot of talk about human bites being worse than dog bites. Probably slightly true. Not much evidence to prove that. I would say probably if I had to choose, I'd go for dog in the developed world, human in the developing world.
In some cases, human bites can be worse than a dog bite, but this is dependent on how deeply the teeth penetrate the skin. There are some nasty bacteria living in our mouths, but populations vary between individuals almost as much as they vary between species. But if your dog has rabies, then you're probably better off being bitten by a person. Many of the infections hospitals see which come from human bites are actually where someone has punched another person in the face, but their skin was broken when it came into contact with the recipient's teeth. And on the forum, Sharky and George said that some of the problem is that people will tend to have their dog bites seen to by a professional, but treat bites from their darling children, for example, at home. Ardy also said that the microorganisms in a dog's mouth are happier colonising dogs than humans, so are probably less likely to infect us following a bite. But on to some altogether more amicable animals now.
This is Sarah from West Sussex. I pass a water meadow each day, and during the winter I've been wondering how the worms cope when it is flooded for days at a time. How do they manage with conditions that range from underwater to baked dry when we have a hot summer? Many thanks.
How do simple worms survive the complex conditions? Let us know your answers by emailing chris@thenakedscientist.com or by writing on the forum at thenakedscientist.com/forum.
Thank you, Diana. That was Diana O'Carroll with our question of the week. Hopefully you'll never be in a situation where you have to choose what to be bitten by. But just in case you are, you know now that you should go for the dog, but do stick to people if rabies might be a factor. That's all we have for this week. Next week we'll be enjoying an Easter break, but we're back after that with another Q&A show. So do keep your questions coming in to us at chris@thenakedscientists.com, unless you're getting in touch through Twitter, where you can tweet @NakedScientists. If you want to catch up with anything we've done, see our experiments, or follow up on any of the news stories we've covered, join us online at thenakedscientists.com. Many thanks to Paul Riley, Jim Hayward and Moshe Alamaro for joining us this week, and to our production team, Mira Senthalingam, Chris Smith, Diana O'Carroll and Tom Simpkins. If you're looking for more science to fill your ears in our absence, then do check out the Naked Astronomy and Naked Archaeology podcasts, both of which are published monthly, and you can find them on thenakedscientists.com or just by searching for them on iTunes. Thank you ever so much for joining us, and we'll be back with more very soon.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.